Hello students, welcome back. Let us resume our discussion on 0 over 0 type limits. And they're here. We completed this problem and that problem. Let me expand the font so that everybody can read this better. Okay. We went through this problem and that problem. How did you do those? By factoring the numerator and denominator and canceling out the common factor. The 0 factor, x minus 2, is common for both numerator and denominator. Cancel those out, and what do we have? This fraction, which is no longer a 0 over 0 type limit. Plug in the value and do your computation, and here's the answer. Make sure you have appropriate limit notations along with all this computation as long as x is there, because this is x part and those are number part. They are not the same. Also, this expression and that expression are the same, yeah, but this and that are not always the same. As a matter of fact, there is a bit of a subtlety there. In any case, it's not good to remove all those limit notation even though answer is correct. You're gonna lose 2, maybe 3 points for doing that. 2 or 3 out of 10, that is. And here's a little bit harder factorization, but still the idea is cancel out the 0 factor. And then once that is done, we have different limit. We have different expression of the same limit. And plug in the numbers and you're gonna get the answer. Now if you throw away all this limit notation, then this function and that function are not the same function. And certainly this is not the same, so everything breaks down and you're going to lose 2 to 3 points out of 10. And if you put all those limit notations here, then everything is perfect. Now let's go over to this problem, and this is of course harder problem. That's because of the square root. How do you handle that? The key is to multiply the conjugate of this. And that's what you used to do when you rationalize a denominator in college algebra, right? And also realize a denominator. We're using the same technique. The conjugate of that is the square root plus 1. Here's the solution. Multiply the conjugate of the numerator to both numerator and denominator, and then apply the expansion formula a minus b times a plus b. And that's a squared minus b squared, as you see in this numerator. Even if you don't see it, if you fold it out and do your computation, you're going to get it eventually. In the end, square root and square cancel each other out. We're going to get much simpler numerator. And after further simplification, h is gone. Now you're ready to plug in numbers, because this is not 0 over 0 type limit anymore. Plug in numbers, do your computation, here's the answer key. So everything is straightforward if you take the first step right. Multiply the conjugate both to numerator and denominator. I admit this is a little harder problem compared with the polynomial over polynomial problem, but I've written this kind of problem in the exam before for a variety of reasons, because number one, we went through this kind of technique before in college algebra, so it's okay to write this kind of problem. Second reason, a little bit bigger reason, this kind of quantity is actually an important quantity called Newton quotient. We're going to talk about those in detail in chapter 3 or module 3, and believe me, this is very, very typical example. Okay, so much for 0 over 0 type limit. Let's go over to infinity over infinity type limits. How do you handle this kind of limit? One way to handle this is to use the limit rule. Take the highest power term and divide each term by that highest order, and then apply the limit rule, and this is a textbook solution. Divide each term by x squared, and then x squared minus x squared divided by x squared, so that just become just constants, so just 2. But all the others have denominators, this one, and that one. And if you use the limit rule, you get 8 over infinity 3 over infinity, 2 over infinity, they all go to 0, and then what's left is 2 over 1. This is perfect solution, but in my opinion, a bit too perfect. So perfect that it's a bit tedious, and then students often end up making mistake trying to do this. So personally, I'd like to discourage students from doing this. I'd much prefer to do it the other way. Find out the growth order of the numerator and denominator. The growth order is second degree. That's the highest order term. The growth order of the denominator is again the second degree. That's the highest order term. How about the lower degree terms? They don't contribute much, so just ignore them, as we did over here. I de-emphasized lower order terms in gray because they do not contribute. My favorite analogy is like this. The highest order term is kind of like amount of water in Pacific Ocean. And then 3x, those kind of things, that's kind of like amount of water you can find in Lake Superior or Mississippi River or things like that. That's a lot compared with finite amount, yeah, but compared with ocean water, pretty much nothing, so you can throw those away. And then what's left is just simple simplification. Cross those out and then you get the answer. It's much easier this way, and then you can cut down mistake a lot better this way. But there's a bit of a warning. If you do not put your limits in right place, this is not right, because this function and that function are totally different functions, and then this right hand side is a number, so you just made 2 equality mistakes actually. So this is going to be either 2 points off or 3 points off out of total 10, depending upon the grading scale. So make sure you have appropriate limit notation as long as you have all the x's in place. Now this limit, you can throw that away as a matter of fact, because I don't have x in there. It's okay to have it, but you can throw it away. But this limit is absolutely necessary. As long as you have x expression in there, you need the limit notation. Let's go to the next problem. You can use the limit rule solution here as well, but I do not recommend it. It's going to be hard. Let's focus upon my suggestion. Let's count the growth order. What's the growth order here? That is, which is the highest order term? This looks like the highest order term, 4th power. Not that one. And that looks like highest order term. And ignore the rest. No, this is not right. This is highest order term, alright, 2nd power. This is not. This is actually 1st degree. It's inside of the square root. The square root is 1/2 power, so this is not highest order term. These actually will have to all go away. And this one will have to stay. It's 2nd order, and smaller order of course will have to go away. And then these will go away. This is not a 4th order, that is actually a 2nd order, because 4th power divided by 2, it's inside of the square root. So you have to be extra careful about those radicals. If you have cubing root, you have to divide by 3. You have to divide by 5 if it's 5th root, and so on. But then again, typographically it's a little bit difficult, and also it's hard enough for square roots, so why would I bother with cubing roots? So I don't usually write cubing root or higher root very often, although I sometimes do. In any case, this is how you do. Highest order is the 2nd order, and this, believe it or not, is a 2nd order. Okay, so what we have, let's remove all these, and remove all these, and let's see, you can further simplify this expression. X to the 4th power, I can take it outside, so x squared, isn't it? I'm having a little bit of difficulty adjusting the bold font, which are not necessary anymore. Okay, alright. And then the next step, I can, not very good. Okay. Let's go ahead and move these and align the equalities, excuse me. Because I expanded fonts, I can no longer fit all those in a single line. I have to do something like this. Okay, that looks better. And here I can factor x squared out, right? And then what's left is square root 2 minus 1. And then x squared down here, up there, they will cancel each other out. And what I'm gonna get is just square root of 2 minus 1, and that's gonna be the answer. I see this kind of mistake a lot. From here, and this is correct answer, maybe I should have made a mistake intentionally so that you could see something. Here, at this step, I see some students doing that. Cancel x squared out, that one out, and then completely that one out, and then conclude this is square root of 2, and this is one of more common mistake. Kind of slipped, but it's a mistake. When you cancel this x squared out, it doesn't become 0, it becomes 1, as you see down here. Better way to protect yourself from this kind of stupid mistake is to factor it out rather than just go heading with crossing. Let's see, do we have enough time for another problem here? Let's try. I don't know whether I'll have enough time, but let's try. Okay, and then this is equal to, let's see, throw away lower order term, throw away lower order term, throw away lower order term. Everything is a first order because second order inside square root, so 2 divided by 2, so this is first order. And get this out of this square root x, and then this is equivalent to, let's see, let's factor x out, and cancel out, you get square root of 2 minus 1 as the final answer. Does it look okay to you? Let's check with Mathematica, and whoa, it's not right. What went wrong? I wish this were classroom so that I have a little bit more lively discussion here. Even if this is not a classroom and you're looking at home, I'll take a bit of time. Please try to find out my mistake here. Where did I make mistake? Lower the terms out, and then got x squared out of the square root, and then factored out, canceled out. What's wrong? Where's the mistake? Obviously we have different answers, something's wrong. Mistake is right here. When I get x squared out of square root, I'm not gonna get x, I'm gonna get negative x here. Why? Because this square root is always positive. Because x is going to negative infinity, this quantity is negative. How do you make a negative quantity into positive? By putting extra negative sign. Here is correct solution. When you get this x squared out of square root, I get extra negative sign. That's because x is going to negative infinity, and this is odd power. If you do that, then you get a little bit different number, and then in the end, you get the right answer. Negative square root of 2 minus 1, as we have in the Tricky, isn't it? That's what happens when x is going to negative infinity and we have odd power. If it is even power, then no problem, because even power is always positive. Odd power and negative infinity, they combine into something special. And in this answer key, I emphasize that part in red. By the way, here is a graphical justification. X is going to positive infinity, we get this horizontal asymptote. X is going to negative infinity, we get the other horizontal asymptote. And this one is negative square root of 2 minus 1. And that one was positive square root of 2 minus 1. We have two different horizontal asymptotes. Toward positive infinity, we have one limit. Toward negative infinity, we have another limit. A little bit tricky, but that's quite natural, and that's commonplace. One more question. When do we have that kind of situation? X is going to negative infinity, that's number 1, and odd power, that's number 2. The growth order is, say, 3, odd power, then you have to worry about that. If the growth order is, say, 4 or 2, no problem there. Even power makes everything positive, so no problem whether x is going to negative infinity or positive infinity. Only those two combinations, odd power and negative infinity, those make this kind of ramification.